All right, ICP class, let's go through some temperature notes. We're going to talk about temperature, what it is a little bit. We're going to unpack it more next week. But for this lesson, we're going to talk about the three scales of temperature. There are more, but we're just going to talk about the three basic ones. And then we're going to go from there. So the first things first is, where's my mouse at? I lost it. There we go. Okay, so what is temperature exactly? So it's a measurement of the kinetic energy in the system. So if we have kinetic energy, we look at kinetic and potential energy. Kinetic energy is the energy of motion, right? So if things are moving at the atomic level, so think about those atoms again. If things are moving, if the atoms are moving at the atomic level, the speed at which they move means for a higher temperature. So we're not going to unpack what thermal energy is, or at least quantify it, but we're going to say that is when things have more thermal energy, those atoms in there are moving more at a higher speed, which then gives you a higher temperature. Now, one thing I'm going to kind of talk about is, heat does not mean the same thing as temperature. We're going to unpack that here in a second, but I'm going to use those words mutually exclusive from each other, where sometimes talking about heat, sometimes we're talking about temperature. And so temperature is a way for us to measure how hot something is, or the energy stored in it. So let's look at this. So when you look at temperature, you have a higher temperature means faster moving particles, means those atoms want to expand, and so those atoms get further apart. So if we have this is called a bimetallic strip, and I have one of these in class, and I can show you to it. But what you do is you're going to take one end of it and you're going to heat it, and so it doesn't really matter which end you heat. And so let's say that there are a couple of atoms. One side's brass, one side's steel. When you heat them up, let's assume that there are the same number of atoms on both sides. Well, the brass side is actually going to expand faster than the steel side. And so the atoms on the steel side are going to be closer together, whereas the atoms on the brass side are going to be further apart. And so this is why when you look at houses, especially old houses, you can't just take steel pipes and marry them up to copper pipes, because copper pipes expand at a different rate than steel pipes. Those would be causing a burst anytime it got too hot or too cold. And so when you look at a building, really, really old buildings particularly tend to have copper pipes, and they tend to be all copper pipes. There is a point where it connects and there's some cast iron, but we're going to leave that there because those joints are really, I would say, complicated to explain. But when you look at old houses, the whole house is usually copper, and you can have bits and pieces changing in there. Now, if we do the same thing and we were to cool it, and so what it is that the brass will shrink faster than the steel, and it'll curve the other direction. And so when we get in class on Tuesday, I'm going to go ahead and show this to you as a demonstration, then I'll unpack it a little bit more. Okay, what are the three ways heat can transfer? So we think of heat as energy, and we think of temperature as a measurement of that energy. How can they transfer? And it's kind of one of three ways. You have conduction, which means it is direct contact, meaning it is touching that object. And so when you go boil some water on the stove, the hot coils are touching the pot, and so the heat in those coils will go to the pan, and the pan will then go to the water, and so the heat there is touching all the time. Another way is convection, and that's kind of when energy is transferred by not necessarily touching it, but kind of a movement of those hotter particles. And so most ovens in a household are convection ovens. And why are they convection? Is because, and when you go and look at an oven, so I'm going to draw this in an oven, we'll call this box an oven. These coils, sometimes you'll have coils at the bottom, sometimes you have coils at the top. These coils cause the air to be warm, and that air, when it circulates, causes your food to get cooked. And so convection is usually also talked about when you're talking about clouds. And so why is it that when you have tornadoes, for example, when you have cool and warm airs coming together, those cause those airs to swirl, and that way, and then creates a tornado. Another thing is, why is there wind? And so wind will always go in the direction of a lower pressure area. Some of that lower pressure is caused by temperature differences, so hot air to cold air. And the last one is radiation. And so electromagnetic radiation is not necessarily the same thing as convection. Convection you can think of as hot air moving and causing something to be warmed up or cooked. Radiation is more specifically looking at when you look at a campfire example and that glow, that orange glow, that is a type of heat being released called black body radiation. Super fun stuff. We really don't get the time to unpack about what black body radiation is, but those are the three types of heat transfer. We're not really going to unpack those a little bit more, but we're just going to talk about what they are, and we're going to keep on moving. Okay. What are the units of temperature? Now, in the United States, we use Fahrenheit. Where did Fahrenheit come from? This guy, Gabriel Fahrenheit, 1714, who was trying to do stuff in his lab, but he was basing it off of the human body. And so the 98.6 is usually a standard temperature for the human body. So at 100 degrees, he said, you know what, the human body we're going to call 100 degrees, and then base it everything off that. And so between the coldest he could make something and the human body, he went from 0 to 100. Now, we have tweaked it just a little bit looking at some other temperatures. Fahrenheit really isn't too helpful when you're looking at science, though, because science really loves to have a standardized thing. And so instead of basing things off of human body, which is subject to change, my temperature might be 98.6 while yours is 98.4 or 97.9. There's a little bit of variance there. So what did we do? Well, a guy about 30 years later came up with the Celsius. Now, Celsius is much better because we now understand 0 degrees Celsius is when water freezes. 32 degrees is kind of an arbitrary random number for water freezing. And 100 degrees is its boiling, whereas 212 degrees is boiling for water. So when we look at stuff, sometimes we're going to convert back and forth, and that's what we're going to do here in a little bit. Is we're going to go from Celsius to Fahrenheit to the third type of Kelvin. And so what we're going to do more often in class is use Celsius because it's easier to understand that temperature range. Okay, what about this third one that we very, very, very much use in science, especially in dealing with gases, which we're going to deal with in about 2 weeks, about the Kelvin. So Kelvin is looking at Celsius in such a way, but for really cold temperatures. And so 0 being absolute 0, the theoretical coldest anything can be. Remember, atoms and solid liquids and gases, solids are, even though they're packed together, they're still vibrating really, really fast. What happens if you go to absolute 0? Then that means those atoms actually stop moving. There is no kinetic energy in the system. There's no heat, there's no movement, nothing can get below absolute 0. Now, there is no understandable limit of how hot something can get, because you can just get warmer and warmer and warmer, but there is a limit to where it's believed you can't get below 0. We've got really close to it with using very specific instrumentation. It is kind of looking at hydrogen atoms and shooting them with lasers. And by shooting with lasers in a certain way, you can actually get it to get colder. Really cool stuff. Maybe it'll be in a reading, but I just want us to know is there is Fahrenheit, which we use in the United States, and boiling is 212 degrees. 32 degrees is the freezing temperature of water, whereas Celsius is much more usable in our science classroom. 100 degrees is boiling, 0 degrees is freezing, and then Kelvin is more of used for gases, because gases move very, very fast, we tend to look at water boils, freezes, and there's an absolute zero, which is 0 Kelvin. So how do we interchange and convert between the three of these? And we have these two formulas right here, is that when converting from Fahrenheit to Celsius, we have these two formulas, which will be always provided on the wall. But there is a third one to play in here, and that's Celsius to Kelvin. You notice that there is no way to go from Fahrenheit straight to Kelvin. That just doesn't exist. So what we're going to do then is we're going to look at a couple examples of going between Celsius and Fahrenheit, and then Celsius and Kelvin, and then maybe even in class we'll do some Fahrenheit to Kelvin. So go ahead, I'm going to go back and forth and reference these formulas on when we are doing this. So let's try this out. Well, this is the first example right here. Go from 59 degrees Fahrenheit to Celsius. So I'm going from Fahrenheit to Celsius. I'm going to use this formula right here. Okay, so what we're going to then say is temperature, I'm going to do T sub F for Fahrenheit, equals 9/5 T plus 32. Now, you could use these equations back and forth. I'll kind of have both for you up there, but let's go ahead and just plug it in. So, actually, you know, we're going from Fahrenheit to Celsius, not Celsius to Fahrenheit. So we're going to use the other formula. Yeah, let's do that. Sorry about that, folks. So we have temperature of Celsius equals 5/9 temperature of Fahrenheit minus 32. Okay, let's plug in our numbers. 5/9 stays 5/9. Temperature of Fahrenheit is going to be 59 minus 32. What is our first thing to do here? Well, I've just plugged in the number we have, which is the temperature in Fahrenheit. And so we're going to do 59 minus 32, because that is in the parentheses. So 59 minus 32, that's, well, actually, no, let's just do it with my calculator. Well, I hate to get something wrong. There we go. 59 minus 32, 27, there we go. And there we go. All right, 5 divided by 9, because 5/9 is 5 divided by 9 times 29, gets me 16.11 degrees Celsius. Okay, let's go from now Celsius to Fahrenheit. Okay. I'm going to zoom out a little bit. Alrighty, so we're going to Fahrenheit, so I'm going to use the Fahrenheit formula. And that's going to be 9/5 T sub C plus 32. Temperature in Fahrenheit, we don't know that. 9/5 T sub C is going to be 25 plus 32. So 9 divided by 5 times 25 is going to get me 45. That sounds about right. Plus 32. 45 plus 32 gives me 77 degrees Fahrenheit. Okay, so we just did one example of going from Fahrenheit to Celsius, Celsius to Fahrenheit. Now let's go from Celsius to Kelvin and the other way around. Now, what we're going to do is we're going to notice that there is a little bit of specific wordage used here when you're looking at 273. There we go. When you're looking at Kelvin, notice that I've written this as degrees Celsius and not degrees Kelvin. So when you're talking in terms of Kelvin, you just say Kelvin. When you're talking in Celsius, you say degrees Celsius. Not quite sure why that is. I'm sure we could look it up, but we're moving on. So I got 100 equals K plus 273. Okay. So now what we're going to do is just subtract 273 on both sides. Get the variable by itself. So Kelvin equals, did I write that down right? Oh, sorry, I did a mistake there. It's not add, subtract. Oops, I knew something was wrong because you can't have negative Kelvin. Getting a little bit ahead of myself. Minus 273. Come on. There we go. I knew something was a little bit off. There we go. So we got 373 Kelvin. Okay, and that's it, folks. Not too bad, as long as you get the formula right. I'm sorry about that. I wrote down the formula wrong. Okay, now let's go 325 Kelvin to Celsius. So we got degrees Celsius equals K minus 273. There we go. Get it right this time. So degrees Celsius equals 325 minus 273. And that's going to get us in the realm of 52. Is that right? 325 minus 273. Hey, look at that. So this is 52 degrees Celsius. Okay, so you notice in here that when you're talking about Fahrenheit, you use degrees Fahrenheit. We're using Celsius, you use degrees Celsius. But when you're talking about Kelvin, you use just Kelvin. Okay, well, guys, if you have any questions for me, absolutely feel free to reach out. I'll see you in class on Tuesday. Okay, I would love to see these notes written down. That way we'll work through some problems. We can work them out together. Okay, that'll be it. Take care, guys.